I'm going to talk about spectral methods, and in particular, I'm going to try to compare and contrast some classical notions of spectral methods, which I'll go over with some more recent modern techniques in the world of spectral methods. And this talk is mainly based on these kind of three seminal textbooks that have to do with numerically computing with functions, really. Two books by Nick Trefethen here, and one book by John Boyd. So if you're interested in lots of details, I'm going to gloss over. These are really amazing references to have on your shelf. Okay, so let's start kind of from where Alex left off yesterday. If you attended his talk, he spoke about what convergence of a method means. And so there are different rates at which a method might converge to a solution. And I'm going to define what I'm going to call a spectral method as a method that converges to the solution as fast as mathematically is allowed. So in particular, this speed is determined by the smoothness of the answer. So a spectral method is really any numerical method whose convergence rate is as fast as the smoothness of the answer will allow it to be. So if my answer has, say, m derivatives, then you get what Alex alluded to as algebraic or nth order convergence, which is like if I'm using n things, n degrees of freedom to represent my answer, then I get order n to the minus m convergence in my error. If my answer is a smoother function, if it's, say, infinitely differentiable, then I'm in the regime of what's called super algebraic, or sometimes people call it sub-geometric convergence, which is that I get an algebraic rate, order n to the minus m, for every value of m. So it's faster than any value of n to the minus m. And if my solution is not only infinitely differentiable, but is in fact an analytic function, then I get geometric or exponential convergence. And now you can see the number of things I'm using to represent my solution, capital N here, is now in the exponent. So it's c to the minus n. And so now as I increase n, that increase is felt in the exponent of c. So you get this exponential convergence for some c that's greater than 1. And so the familiar plots that Alex alluded to, like a log-log plot, and this is taken from the third reference that I alluded to, John Boyd's book. On a log-log plot, my algebraic convergence, or my nth order convergence, looks like a straight line. But if my function is smooth, I could get error convergence that is much faster than a straight line, this geometric or sub-geometric or super geometric convergence. And on a log linear plot, so this is kind of the more difficult plot to get a straight line on, an nth order convergence scheme will look like this kind of slowly decaying curve, whereas these geometric ones will look like straight lines on a log linear plot. And so we call accuracy that's as good as the function will allow spectral accuracy. And so this is what I mean when I say a spectral method. And so numerically computing to try to get spectral accuracy is really all about how you want to represent a function on a computer. And so there are a few ways we could do it. I'm going to focus on kind of two schools of thought. So suppose we're approximating a function, u of x, defined on the interval -1 to 1. So how should we discretize this so we can compute with it to spectral accuracy, to an accuracy that's as fast as is allowed by the solution? So I could put down some grid points and represent my function as values on a grid. One way to think about this is through what are called Lagrange polynomials. I can define a polynomial, little l, that is 1 at one of my grid points, say this red node here, and is 0 at all of the others. So that's the kth Lagrange polynomial. Each grid point gets its own Lagrange polynomial, and this is just a polynomial that interpolates through the nodes and is 0 at all of them except for 1. And then these little u of k's, if I want to represent my function as a sum of these Lagrange polynomials, they're just the values of u at these nodes. And so this is kind of what I'm going to refer to as the value-based approach to spectral methods. And sometimes you'll hear words like pseudospectral, nodal, collocation. These all mean you're living on a grid somewhere. Alternatively, you could represent your function, instead of using values on a grid, as coefficients in some more general expansion of functions. So I could have some family of, say, orthogonal polynomials, phi, think of, say, Fourier series, and now these coefficients in the sum u hat are just the inner product of my function with my orthogonal polynomials. And so here I've just shown Fourier series, and my unknowns here are no longer values on a grid, they're how much I'm going to weight each of my phi k's in this sum. And so you'll sometimes hear words like spectral, modal, frequency domain. These all mean you're kind of living in coefficient space. And the world of kind of fast transforms, you might have heard of the fast Fourier transform, is all about kind of how to go between these two spaces, how to go from values on a grid to coefficients in an expansion, how to go from coefficients in an expansion to values on a grid. Okay, so I want to compute with these things maybe in one of these two representations. So how should I choose my grid points to represent my function if I want to work in values? Or how should I choose my basis functions, phi, if I want to work in coefficients? Well, it turns out if your function is periodic, as you probably know, Fourier series are the right choice to represent a periodic function. And if you want to work in values, it's very simple. You can just work on equally spaced grids of values. If your function is non-periodic, you have to be a bit more careful if you try to discretize your function on an equally spaced grid, just like in the periodic case. What will end up happening is you'll see these kind of oscillations at the endpoints, and this is what's known as the Runge phenomenon. And so to fix this, the kind of classical approach for non-periodic functions is to use a Chebyshev grid or a Chebyshev series. And these are really just the non-periodic analog of a Fourier series. So if you think about a cylinder here on the bottom right, and I draw a Fourier series on the surface of the cylinder, the kind of surface of the cylinder is nice and periodic, so Fourier series work well. But the shadow of the cylinder, the projection of the cylinder onto the interval -1, 1 down here, are the Chebyshev polynomials. And so it's kind of just the non-periodic shadow of the Fourier series. And that's what they look like here, and these are what the grids look like if you want to work in values. Okay, so we have these two representations, either on a grid or in terms of orthogonal polynomials. And once we have this representation, many operations are very easy. We can just apply the operation to each term in this sum. And so to get a flavor of each representation, I just want to highlight what it looks like to take a derivative in each of these worlds, in the values world and in the coefficients world. And in particular, we're going to look at a traditional take and a more modern take on each one. So first, let's talk about value-based spectral methods. So we're living in the world of a grid. We have Lagrange polynomials, and these UKs are just the value of my function u at each of these grid points. Okay, so we want to take a derivative. Say we're in the non-periodic world. We're on a Chebyshev grid, so we have points x0 to xn. And I have some function values here in red, u at x0 to u at xn. And because we're in value space, I'm representing this red curve as just the interpolant through all of these red points, which is just the representation from the last slide, the sum of the values times the Lagrange polynomials. And once we have this representation, you can take a derivative quite easily. You just take the interpolant here and go term by term and take the derivative of each of these Lagrange polynomials. This gives you another polynomial, this blue curve. And now if I want the value of the blue curve at the blue points, I'm going to have to evaluate this sum at each of the x0 to xn. And so in practice, what does this mean? If I have, say, n of these points, and I want to represent differentiation as an operation between endpoints to endpoints, well, the value of my derivative at the jth point, well, that's just this sum. It's the original values times the derivative of the Lagrange polynomial at the jth point. But now I want to represent this kind of in the same world that I started in. So I want to represent this back in the Lagrange polynomial basis of the original grid. And so this is going to be some other sum of some u primes in terms of Lagrange polynomials. And what this really means, if I want to evaluate the derivative at the jth point, in order to do it, I have to take an interpolant through all the points, evaluate the derivative of that interpolant, and then read off the value of the derivative. And so this is really an all-to-all kind of operation at the kth point. And so this means that I can write down a matrix D that just takes in n values and gives me back n values of the derivative. And so I'm going to call this a differentiation matrix. That's kind of the classical take on how to take a derivative on a grid using a spectral method. The modern take that I'm going to talk about is due to Toby Driscoll and Nick Hale from 2015. And so they noticed that, you know, if you take a derivative of a degree n polynomial, you know that you get back a degree n minus 1 polynomial. And so instead of thinking about taking a derivative on a grid and representing its answer on the same grid, we should really think about representing its answer on a grid with one less point. So this matrix D should really map from an n plus 1 point grid to an n point grid. And so what this means is that really differentiation is not a square matrix, it's a rectangular matrix. And if I have some sort of resampling matrix, which takes my n plus 1 point grid and maps it to an n point grid, then this operation of rectangular differentiation is just my traditional classical view of spectral differentiation on the grid times something that resamples from the n plus 1 point grid to the n point grid. And so you might ask, why is this useful? Well, it's useful when you start thinking about how boundary conditions should be imposed if you want to solve, say, an ODE. So if we consider the ODE, u prime plus AU equals F, with a boundary condition at the left endpoint, u at minus 1 equals C. Well, okay, traditional kind of spectral differentiation would say, okay, I'm going to take my differentiation matrix on the n plus 1 point grid, that's Dn, plus a matrix that just point-wise multiplies the values of A at x0 through xn times the values of u at x0 through xn. And now my right-hand side f in this ODE is just the values of f at x0 to xn. So this is the action of the differential operator, L times u. And then this boundary condition, u at minus 1 equals c. Well, we have the values of u on the interval minus 1 to 1. x0 is equal to minus 1. That's the left endpoint. And so I can impose this boundary condition by just taking the left value and setting it to c. And so this ODE can be written as this block matrix B over L times U equals C over F, where this top part imposed the boundary conditions and the bottom part was the differential operator. But in this traditional view of spectral differentiation, this system is actually rectangular. So because D was square, L is square, and my boundary condition is one row. And so this is square with a row on top. And so this is rectangular by one too many for me to solve. So I'd like to delete a row. Anyone want to suggest what row I might delete from this? Okay, well, you could say, let's just delete the first row. That corresponds to the grid point at the left. I'm imposing a boundary condition on the left. So I'm just going to cross that out, take all the ones below it, and put my boundary condition where that was. And while maybe this is natural for this example, if you have a more complicated boundary condition that's not just a value at a left endpoint, but it's, say, an integral constraint or a sum of two values, then it's really unclear in physical space what row you should get rid of. If you take this rectangular view of differentiation, you have the same linear system as above. L started out as square, but now you just multiply it by a projection matrix, which takes you from an n+1 point grid to an n point grid. This is now rectangular in width. So it has space for exactly one row because this rectangular matrix mapped us down a degree. And so we have precisely the space we need to make this system square. And so this is one of the very appealing ways of taking a derivative in a modern spectral method. Robert.
Can I ask just one question? So what you want to delete a row to make it square?
Yes.
Because otherwise there isn't a solution.
I mean, you could take a least squares solution.
Well, that's my question. Why not just take a least squares solution?
You could, and sometimes that'll work, and sometimes you won't get the spectral accuracy that you expect.
I see. Okay.
Yeah. No, so, yeah, so, I mean, in this last example, right, I'm imposing a PDE on a grid. I have a boundary condition at one of the grid points. And I'm imposing the differential operator at all of the grid points. So you could say, naturally, the row I should delete is the one at which I'm imposing the boundary condition, the grid point on the left. The operator P. So the operator P, yeah, so the operator P is just, you could think of it as like a barycentric interpolation. You just go from an n+1 point grid to an n point grid. And you can just write down what the interpolant is from the higher order grid to the lower order grid. So it's something that you can just write down. It's not random. And so in practice, this looks like this system with a boundary condition on top and then this differentiation operator on the bottom. This looks like a dense matrix with a row on top corresponding to the boundary condition. And so this is kind of traditional or kind of expected of value-based spectral methods that you'll get a dense linear system. And so this is my Drake summary of Driscoll-Hale 2015. Differentiation really isn't a square matrix, it's a rectangular matrix if you consider the degree of the polynomials. Coefficient-based methods now are going to take a different approach. I'm going to represent my function as an orthogonal polynomial expansion, phi k times u hats. And I'm going to ask the same question. Given coefficients in this expansion, in the basis, what are the coefficients of the derivative in that same expansion? So let's start with an easy case. Okay, if u is a periodic function on -1, 1, we can represent it with a Fourier series. So phi is e to the I pi kx. U is now just a sum of Fourier coefficients times e to the I pi kx. And we probably all know that taking a derivative in Fourier space is very easy. The derivative is a sparse operation because if I just substitute in what the basis function is, I take the derivative of each basis function, I get back e to the I pi kx times a prefactor times I pi k. And so the coefficients of my derivative are just the coefficients of my original function times I pi k. And so this is very nice. The kth coefficient of the derivative depends only on the kth coefficient of the original function. Okay, so let's try to do this in the non-periodic setting. Oh, and this means that we can just write down a diagonal matrix, which just scales exactly by I pi k, each of the Fourier coefficients, to get the derivative. Okay, so in the non-periodic setting now, I'm going to represent my function as an expansion in Chebyshev polynomials. But now if I go look at if there's a nice representation of the derivative of a Chebyshev polynomial in terms of Chebyshev polynomials, well, there's not really this nice sparse property that you get back the same polynomial that you started with. Kind of the derivative of the kth Chebyshev polynomial, if you expand it in terms of Chebyshev polynomials again, you have to use many of them. You have to use either all the odd ones or all the even ones. So this is not really a sparse operation. But the modern take on non-periodic coefficient-based differentiation is called ultraspherical differentiation. And the trick is, let's just let the operation of taking a derivative just change the basis that we're living in. And so if you go to the NIST Digital Library of Mathematical Functions and you look up identities for various families of orthogonal polynomials, you'll find a table that looks like this. If I take a derivative of a Chebyshev polynomial, well, it has this nice property that I get back a single polynomial. So tk maps to ck minus 1, where c is called an ultraspherical polynomial of parameter 1. Now, this is kind of a general family of polynomials that are kind of a special case of Jacobi polynomials. But it's just another family of orthogonal polynomials that we could compute with, and we could happily live in this space. And so this is nice because if I take the derivative of the kth one, I get back the k minus first one times a prefactor. If I take two derivatives, I get back the k minus second one times a prefactor. And so I no longer have this spreading of a derivative of one thing had to be represented in all things. So the operation of taking a derivative from Chebyshev to this special ultraspherical space is a sparse operation. And this was really pioneered by Shianover and Alex Townsend in 2012. So what does this mean? Okay, I can write down what this relation means in matrix form. It's not a diagonal matrix like Fourier. It's diagonal shifted by 1 because of this k minus 1 down here. You can also convert between these spaces. So Chebyshev polynomials have a nice representation in the family that you ended up in after taking a derivative. Ultraspherical polynomials of parameter 1, say, have this banded structure. And if I want to multiply two functions, you might think, okay, well, multiplying two degree n polynomials, representing that as a degree n polynomial, that's not a very sparse thing. But if one of them is low degree, say it's m degree, then you get a banded matrix whose bandwidth is dependent on m. So if I go back to my ODE here, I can write down the same action of the differential operator on my coefficients, but now I use these ultraspherical differentiation matrices. So I take a derivative. Here I have a matrix which represents multiplication in coefficient space. But now because I took a derivative, I mapped from Chebyshev coefficients. When I took a derivative, I landed in ultraspherical coefficients. Here, I now have to upgrade this term, which mapped from Chebyshev coefficients to Chebyshev coefficients. I have to convert those up to match the derivative from Chebyshev coefficients to ultraspherical coefficients. And same with my right-hand side here. I have Chebyshev coefficients of f. This left-hand side here now all lives in this CK space. So I have to upgrade the space of the right-hand side. And if you kind of come from the finite element world, you might think of using different test and trial functions, like in a Petrov-Galerkin scheme or something. This is the same idea. My boundary condition is now no longer just taking a value at the left endpoint. It's evaluating a set of Chebyshev polynomials at the left endpoint. But I get the same block system. Now the system is also rectangular, but the nice thing about coefficient space is that rectangular differentiation is automatically represented. So the last row of this, L, is actually all zeros because we took a derivative. So I can just take off that last row and I end up with a square system. And because we have these nice recurrence relations between Chebyshev and these other spaces of functions, we get a much sparser linear system where it's now banded with a dense row that imposes the boundary conditions. So this is Drake's summary of Ulver-Townsend. If I take a derivative of Chebyshev and I try to represent it in Chebyshev coefficients, I kind of get a dense operation. If I take a derivative of Chebyshev and I represent it in a different function space, ultraspherical coefficients, it's a much sparser operation. So when should I use one or the other? Well, multiplication on a grid is inherently local. It's very easy to do point by point. Multiplication can be global, though, in the space of these coefficients. However, taking a derivative on the grid is inherently global because I have to form an interpolant over all grid points. But taking a derivative can be local, as we just saw, in coefficient space if you work in the right space of functions. Working on a grid using collocation is often ill-conditioned, but coefficient-based methods can be well-conditioned. They can also be sparse, as we just saw, but if the degree of the variable coefficients, say, in your ODE is very high, then this sparsity is probably lost. And so the best of both worlds might be something like time-stepping with an IMEX scheme, where you might have some linear terms, like a diffusion term, which can be solved very efficiently, implicitly using coefficients. You can then transform to the grid to value space, evaluate things like nonlinear terms like reaction or advection explicitly using values, and then transform back to coefficients. So trying to get the best of both worlds is really what this is all about. There's lots of software that you should really try to check out if you're interested. ChebFun and MATLAB is just really a fun tool to play around with, and there's powerful analogs of it in both Python and Julia. The Daedalus project in particular really has taken spectral methods to the kind of high performance computing worlds and to the astrophysical fluids world. And here are just, some various applications of these ideas. So just because these things are on simple geometries maybe doesn't necessarily mean that they aren't useful. So this is from the Daedalus project, very high Reynolds number fluid flow. This is from Slavinsky and Ulver, very high frequency scattering. This is some work that I've done on kind of trying to adapt these very high order spectral methods in a piecewise fashion on patches to couple them together on complex geometries. And if you have interesting shapes, you can do similar things. This is a project that I've done with Leslie and Pearson Miller in CCB and Stoss in CCB on simulating cell polarization on various curved surfaces. Some things I didn't mention, well, this was in 1D. Simple 2D and 3D geometries also work well. You can use tensor products of 1D ideas or special basis functions like spherical harmonics, Zernike polynomials, etc. More complex geometries, you can try to patch things together into a mesh, use an element method, some piecewise spectral scheme. And this was entirely focused on the idea of differentiation and differential equations, but you could entirely reformulate everything in terms of integration and integral equations, and the same ideas really apply. And there are lots of kind of spectral experts here at Flatiron, and so if you have a problem that you think might be suitable for a spectral method, please come talk to us. Thank you.
Any questions? I'll ask a hard question then. Do I want to ask a hard question? Yes. So in the 1D case, for the methods that you said, if you want to be adaptive, how do you have to modify those methods?
Yeah. So you can do piecewise things. You could split intervals into sub-intervals, and you could impose either in value space, you could put a grid on each sub-interval or coefficients on each sub-interval, and impose, say, continuity of the derivative conditions between each of those patches. You kind of lose the global spectral accuracy at the expense of adaptivity, but then you can go to the realm of sort of HP adaptivity and see, you know, I could refine my grid where maybe there are shocks or discontinuities in the solution where a global kind of smooth function is not the right representation.
The question was how to use spectral methods on those complicated geometries.
Sure. Yeah. Okay. So in 1D, it's easy. In 2D on a square, you can take a tensor product of 1D things. You could think the same ideas might apply. Okay, and now you could think about taking two squares and gluing them together. Okay, on each of those squares, it's entirely what I presented essentially, but in tensor product form. And now you have an extra condition between the two squares that impose continuity of some higher order values between those two squares. Okay, now instead of squares, you could think about quadrilaterals. There's some coordinate transformation that maps a square to a quadrilateral. You can then do the same idea of gluing two quadrilaterals together, and then you can almost kind of in the recursive skeletonization fashion that Leslie presented yesterday, you can kind of glue two things in a hierarchical fashion. So I could take two quadrilaterals, glue them to two others, then take those two quadrilaterals that were just glued and glue those pairs together and go kind of up this tree of patches. Nothing dependent on it being a simple geometry. It's just simple from the perspective of each of the quadrilaterals.
It's finite elements?
It essentially is a finite element method. It's just, you could think about a second order finite element method, a 10th order finite element method. This used 50th order on some of these large patches.
So what makes it a spectral method? I'm a bit lost.
So the spectral method
if your bases are local.
The bases are local, but if you actually look at the convergence to the solution, you still get exponential convergence if you do the right thing with your degrees of freedom.
Yes.
If you spend your degrees of freedom near where there are corner singularities and things that might restrict your spectral accuracy, if you use lots of small elements there to kind of localize the effects of those corner singularities from the interior, then you're free to use higher order elements inside. Mm-hmm. And there's this whole theory of HP adaptive finite element methods, which tells you how to do this, how to spend your degrees of freedom to get still exponential convergence to your solution.
Thank you.